Check. Check. Check, 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 test. Check, check.
One, two, three. Check, check.
Good. If you want everyone to mute it. If they levels, I'll test it all.
Hi, Karen from the museum. Thank you for doing this. Can't wait to hear what you're going to say. I don't know about the glacial rate of change.
Just
I have a feeling this is going to be a good talk. I love it when people talk about why history matters.
okay. Well, thank you.
Ladies and gentlemen, while we're waiting to get started, it'll be a few more minutes. I might point out you've got a questionnaire in your seat, and we periodically do some surveys just so we can get some feedback from you, the folks that come to our programs. And if you take a moment to just fill that out, even if you filled them out in the past, we do these periodically, and it kind of characterizes the audience and helps us develop the profiles that we really want to be able to do and to serve you better. And say anything you'd like. Thank you very much. minutes.
Okay.
So ladies and gentlemen, welcome to this evening's presentation. We've got a great evening in store for you. I'm John Toole, the Executive Director and CEO of the Computer History Museum. I would like to ask, how many people have been here actually for the very first time, the Computer History Museum? It's a lot of new people. Well, welcome. I hope you're going to have a great evening with Greg Papadopoulos and a few things. I'd like to offer a couple of remarks about the Computer History Museum for those that have not been here before, but more fundamentally, I'd like to share with you some of our beginnings. Last week, we actually celebrated our 25th anniversary organizationally in some of our collection. Dates back that long. According to when Bell established the Computer Museum, Digital Computer Museum actually, in the headquarters of Digital Equipment Corporation 25 years ago. And it's a very special time for us. That was the birthday cake down there, lower left. And they moved to the Boston Wharf. Some of you probably remember the Computer Museum when it was part of the Museum of Science. And then later on, we camped out with the collection, brought it westward, thanks to people like Len Shustik, who's our chairman of the board, who's here this evening, at NASA Ames. And from there, we moved and opened our first phase. And this is only our first phase of the Computer History Museum, serving the mission of preserving the artifacts and stories of the information age on June 2nd, 2003. I really do hope you've had an opportunity to visit our visible storage exhibit downstairs. This is a first step. Some people have characterized it as a warehouse on steroids or a warehouse with labels. It's not a complete museum yet. And that's what happened in our second and third phases as time goes on. But we've also got things that, because we're not satisfied with what we have, and we're moving forward. I think this group particularly would be interested to know that we're going to be putting a small software exhibit. How do you exhibit software? What topics should you choose? How are you going to make this compelling to both the audiences that we have? This is what our challenge is, and we're going to have that probably available for you next June. It'll be the software history of chess is the topic that we've chosen. And it'll give us an opportunity to really look carefully and deeply about some of the programming and algorithms along the way. And we're pretty excited about it, and it's just one of the things, plus the public programs for which we have. The second big thing that I really want to talk about this evening, before I introduce Glenn Edens, who will introduce our speaker, is really the partnership that we've got with Sun Microsystems. And today is the inaugural lecture of the Odysseys in Technology series. It's really a year-long, 10-event collaboration between Sun Labs and the Computer History Museum that presents people and perspectives behind extraordinary innovations and advancements in the computer technology-related world. Brings the technology and the people. And I think you're going to find this to be a phenomenal series as we go forward. And someone asked me this evening, what are the next series of lectures on this? We haven't had much time to publicize it. But you'll be hearing a lot more within Sun. You'll hear a lot more in the newspapers, and the particular lectures that will be coming up. October 20th is our next one with Nicholas Wirth, who will also be one of our museum fellows inducted the evening before. November 3rd with Bill Morgridge, and December 14th about computers and music. So we've got quite a start of a collaboration. It's going to be a phenomenal time, and again, I want to thank Sun Labs for the wonderful work they've been doing in collaboration. They've been working with us. The museum also has a series of lectures and events that I just want to bring you up to speed on. This Friday, October 1st, Bill Gates will be here. It's pretty well sold out, but look online if there may be some opportunities to attend. Steve Case will be here in January. Our big event of the year, from our point of view, is the 2004 Fellows Awards. We're honoring Eric Bloch, Bob Evans, who unfortunately passed away a few weeks ago. So this will be given to him posthumously. Dan Bricklin, Bob Frankston for VisiCalc, and Nicholas Firth for all his contributions. And this is going to be a fun, elegant evening that I think anyone who is interested, or additional sponsors that you may want to bring to us for that event, it's still open, and Karen Tucker here was the person that you could contact if you're interested. And we also have another kinds of different types of lectures. We're putting together a program called Stump the Historians. We're very, very fortunate to have the IEEE Annals of History of Computing being here on November 19th in conjunction with a series of oral histories that we're doing and a business meeting that they're having. And they agreed to come up and talk about how historians see the future of computing in the future. And plus, it'll be a terrific opportunity to come loaded with your questions to try to stump the historians. So I think you'll really enjoy that. Now I'd like to introduce Glenn Edens, who's really a renowned researcher in so many different ways and has extensive background, an entrepreneur, corporate strategist, and consultant in telecommunications, entertainment, and computer technology design. At Sun, he's currently Vice President and Director of Sun Microsystems Laboratories and manages 3 different laboratories in Mountain View, Burlington, Massachusetts, and Grenoble, France. Prior to joining Sun, he worked for AT&T Strategic Ventures and also served as VP of Broadband Technology for AT&T Labs. In 1985, Glenn founded Waveframe Corporation, which developed the first all-digital audio workstations for the motion picture, television, and recording industries worldwide. On top of this, he co-founded Grid Computer Systems. So you can tell that at heart, he's as much of a geek as some of the rest of us happen to be. And he served on several boards of directors of nonprofits and public corporations. And he's also very famous for having been a co-recipient of an Oscar for his work in digital audio. So we're a little bit jealous of that, but we're working on that over time. Ladies and gentlemen, Glenn Edens.
We're actually still arguing over who gets the Oscar. Because it turns out they give it to the company, not the individuals, which is pretty interesting. It's my privilege tonight to introduce Greg Papadopoulos. So we're having a lot of introductions tonight. So I will do my share and try to be brief. This is kind of an interesting thing for me to do because I have the honor of working for Greg, so it's really important that I don't screw this up. There's another interesting event that Greg joined Sun in 1994. So this is Greg's 10th anniversary year with Sun, which I believe is the minimum qualification for a historical event, as defined by the Computer History Museum. So I wanted to go over a little bit of Greg's background. Greg is currently Executive Vice President and Chief Technology Officer for Sun Microsystems. And Greg will tell you a little bit more about the scope of his work at Sun. He's held a number of engineering management positions within Sun. And prior to joining Sun, he was the senior architect and director of strategy for thinking machines. And he was one of the developers of the CM5 supercomputer. Greg is also assistant professor of electrical engineering and computer science at MIT. His degrees are, first, let me find that page. BA from System Science from the University of California at San Diego, kind of a party school. But then he got serious and went to get his both Masters of Science and PhD in electrical engineering and computer science from MIT. Greg also serves on a couple of very interesting boards of directors, British Petroleum, and also the Anita Borg Institute for Women in Technology, and one that I also think is very interesting, which is SETI, the Search for Extraterrestrial Intelligence. So with that, Greg.
Thank you, John. Thank
Please.
you. Appreciate it. Well, this is really a lot of fun. And I actually thank you, John, and the museum here for giving me this opportunity to give the talk. And let me Let me try to frame this for you a little bit. Actually, everybody who I've told the title to sort of breaks out in a little bit of a smile. You know, it's a bit of this, yeah, right, things aren't really changing as fast as we think they are. So what is sort of the, if you will, the environment I want to have you sort of thinking about or sitting in for the next hour, and then we'll do, I think, some questions afterwards. So, you know, anything and everything after that. But I was sort of asked to give this talk from a personal perspective, but also in a way of trying to document what our living history is, because we're all of the, you know, the generations here that really are at the founding of the computer revolution and communications revolution. And I just think this museum is just a phenomenal thing to happen now, and to, you know, try to preserve and curate as much as we can. And so the perspective that I was asked to give is, think of an historian 100 or 150 years from now going back and listening to this talk and many other talks here, trying to reconstruct history, what really happened. Okay, so there's a bit of honoring history here. So and I will get very geeky at times, and people who are in sort of the architectural end of things may resonate with that. I'm going to try to get out of being totally nerdly about it and communicate some bigger things. But as much as I think, you know, one of the themes here is that actually computing technology moves very slowly. We are at a point that's really, from my point of view, very interesting, and it's a point that has, you know, happens every 10 or 15 years, and we look like we may even be at a 20-year kind of point in the business, and that's a long time in computing to see a big change come about. So, without further apologies, I thought I would start with just a little bit of credentials, because since '94, you know, I haven't held an honest job as an architect. You'll see that stuff sort of grayed out because I was doing more of the strategic things, and coincidentally, my hair started to turn gray in '94 as well, as you'll see. But before then, you know, basically, I started as a control systems engineer. So my first job was with HP. I worked on the paper moving plotter controls, and got recruited by Honeywell, and worked on one of the very first microprocessor flight control systems in the early '80s. Fault tolerant work from that, actually heavily influenced by work that Leslie Lamport had done at SRI. And you know, and I'll tell you something very frightening. So I worked on essentially what the communications architecture was and the voting architecture that is the standard on the 777 right now. Right? So I'm not sure I want to fly on the plane anymore. And then got a fellowship with Draper to work on their fault-tolerant processor. A lot of things, was a co-founder of PictureTel, and I actually have an artifact from there to try to show you some of the technology that was done at that point in time. I also left PictureTel and started a company called AI Architects, later called Ergo Computing, and we built the first 386 computer in the world. It was something called the Hummingbird, which was an add-in 386. In fact, we were really close with Intel to doing this great PR thing until they woke up and figured out we were only a 5-person company in Cambridge, and Compaq may have something to say about that announcement. But then, you know, was in sort of the high-performance computing business for quite some time, and I'll reflect on that a lot, because I think that a lot of the influences in computer architecture really did come from people trying to solve some hard scientific problems. And if there's anything that you get out of this talk, we're going to be returning to a period of time where solving some very hard physical problems are be very important to us, and I think is going to redrive a lot of architectural thinking. And just for people who like to collect machines, I've actually done a lot of hacking in my life, both for fun and for profit, and some of it less. I did actually, this Burroughs 6700 system, I actually did crack it, and that was really a lot of fun hacking. But I also, as you look at a list like this, and it sort of surprised me to go through it myself and kind of put it together, it sort of stops, you know, around 1990, if people know the dates on a lot of these things, because after that it kind of got plain again. And that's one of the messages here, right? This was my computer in 1978. That's actually the 1979 version of it. I didn't have a floppy disk on it. But this was built with the 6502 microprocessor, the same thing that was in the Apple. Unfortunately, they came out within a few months of the Apple II, so that company, Ohio Scientific, went out of business. But here's something that kind of to make the main point of the talk here, right? And this may sound a little bit of a negative point, but this is a reasonably modern microprocessor design or processor design for people who follow this stuff. 64-bit, so we're all, hearing that the big thing in computing is moving from 32 to 64-bit, and with Optron and now with Nocona, and basically the whole world has moved to that. Being able to issue 7 instructions at a time, so you can grab seven different operations, execute them, finish them out of order. Basically things that are quite aggressive and modern. And I might also add that the team here, which is a 25-person team actually that started against this design, was just right up the road here, so a Silicon Valley contribution. If people want to get it a little more dated, a 10 nanosecond cycle time was the design goal. Okay, so that's 100 megahertz. And we're now at a few gigahertz, but 100 megahertz, in 1995, if this design got completed in 1995, that would be a very competitive system. Right? They would sell a lot of chips with that. You must know the punchline here, right? This is what was being worked on Kuiper Road in 1965. It was part of a very secret project at IBM that has only fairly recently come out into the open that they were working on it. But this was the ACS-1 that then became the ACS-360, was never built, but pioneered a lot of these concepts, and a lot of the greats in the field were part of it. So you kind of got to look at this for a minute, and you got to pause and wonder, what the heck have we been doing for the past 40 years? All right? So the basic thesis is something that I hope actually through this is not supposed to be negative. It's actually supposed to be about understanding and celebrating the history and not forgetting it, because it is in fact what defines computing. So one thing is that we do tend to exaggerate the advances in computing by confusing architecture with technology. Right? We see technology move very quickly, so we think computing is moving very quickly. In fact, it's not. And in fact, if you even take things of your own experience, I could open up your PC now and go find code, in the BIOS of that machine that I was hacking on in 1983. Right? Exactly the same BIOS code is there for legacy reasons. There's an aside here, is that we also exaggerate the advances in technology, because we get confused with things that run fast with miniaturization. Moore's law is something about miniaturization, as it turns out. Okay, and I'll try to make that point in a minute. And if I get in a negative state, and how I felt a bit for particularly the sort of more advanced architectural thinking, is that in fact the advances of technology have made architecture advancement a whole lot harder. Right? And I'll go reflect on that too. So that might be a surprising thing, that if the technology moves so fast, it may in fact make it more and more difficult to innovate in architecture. So here's a little bit of analysis to do this Moore's law caution. Right? So I'm going to step you through this, because I think it's important to kind of understand when we throw this law around of something doubling every 18 months, what do we mean? So I've taken two systems here. There's 1967, the 36091, definitely a landmark system in terms of architectural concepts. And then a sort of a composite microprocessor from this year. So it's kind of blending things like an Optron and a Xeon and a Power and a Spark system together. And you get this, you can look at things like what's the cycle time of 60 nanoseconds. So, that's a little bit, what is it, 16 megahertz or 17 megahertz to basically a quarter of a nanosecond, or excuse me, did I get the You know, right, that's 400 megahertz. I got to put another decimal place in there. Sorry about that. This talk I'm giving once now. So that's a factor of 2,500, actually. No, do I have it right? Oh, that's right. No, I do have it right. OK, thank you. See, I'm tired. I'm doing this on the fly. I got it right. It's 4 gigahertz. All right. I was panicking that I didn't do my math right on this. That would be embarrassing. All right, I'll save it. Flops was about 10 megaflops to 5 gigaflops is what you do today. RAM, 6 megabytes to 8 gigabytes. There was 300 megabytes of drum storage on that 91. That is a tremendous amount of storage in that day. And actually, this 750 gigabytes and 8 gig is the Apple G5 X server, which I think is a really pretty package. And then these are the, sort of the number of transistors, 100,000 to 100 million. So those are the factors. All right? And it's kind of a factor of 1,000-ish. It's nothing to sneeze at. Okay, but if you do the Moore's law calculation, because integrated circuits started right there, 1967. That's kind of one of the base years of this calculation. 2 to the 24th, right, is about how many doubling times there are. Say it's 18 months doubling time. So you expect to see a factor more like 16 million. What happened? No. You multiply all of them together is the answer. I guess it does that. No, but the fact is that there is a machine, right? If you measure that as performance, it's only 500 times. Doesn't look very good to me. So what's the bug here? And what's going on? You didn't put dollars on it. I didn't put dollars. Exactly. Yep. It's actually not 16 million times cheaper. I can guarantee you that too. All right? So here we go. This is the technology that IBM used to construct the machine, this is a really beautiful year to study in computing technology, 67, because it was just the beginning of the integrated circuit. And this is not integrated circuits. There are up to 2 transistors that fit on a chip in this design. But these are very well-crafted, basically hybrid modules. Okay? And they're about half a watt. And you can get about 20 transistors, 30 transistors equivalently on one of these modules. Beautiful piece of engineering. And of course, you use lots of these to go build the computer. That's the answer. Right? And the answer is it's about density. From 20 transistors on a chip, essentially a module, to 100 million transistors, there's our Moore's law. 20 million times. So what happens is that whole machine's been reduced, it's been miniaturized. And it's gotten faster, which is good, because physics, it's nice when you go shrink things down and get it faster. That's what's going on there. So the first example is one about, hey, architecture really hasn't moved that much. The second one is, don't think that computers are doubling in speed every 18 months compared to what you could design, or what has been designed. Because there were some really fast machines. Seymour Cray, 20 years ago, was pushing a 2 nanosecond cycle time, right? Very close to the kinds of things that we're doing today. But it's what is the miniaturization and cost of that? Probably. But it's close enough, because it could have been 5 transistors on it. Thank you. So I think that there are only, basically 5 architectural ideas that, and I think about what really has gone on in people's thinking since von Neumann, essentially, is that, there have been these kinds of basic pieces of insight and innovation, and fundamentally we go explore these areas and we do variations and we keep re-implementing them. Right? And I really don't think there's a whole lot more than this that's going on. Indirection was one of the very simplest and most important ideas in making these general purpose machines work, which was, you don't just can name the location literally. I want to see what's in location 1023, but in fact I can have a value that I get to compute what location I want to look at, right? And indirect, look at that as an indirection. And I think a lot of that first stuff, was was really, Wheeler had done that on EDSAC with self-modifying code. It was, those basic kinds of pieces of innovation. Really sort of indirection in my mind is the most important one on here. If you then say interpretation is the whole idea of microcode, right? That I can build one machine and make it look like a different one, because that one machine runs its own program. And so microcoding was that art, and I, in my mind, it's Morris Wilks who really is the guy who thought about that and drove a lot of the thinking about how do you design one machine that gets to behave like it's another. Caching is the basic idea of replication, right? That if we think that there's a value that we want to share, and we can each continue to go to that location, or we can make copies of it. And you see of course the basic hazard of making a copy of something, that if I changed my copy of it, how do I inform you? Right? And what are the sort of guarantees about when I inform you and how do I inform you relative to other things I do? So there are many, I would say probably thousands of PhDs that have been minted on that one topic alone. But it's also one that at the scale of the internet is a very relevant architectural idea. Virtualization is subtly different than interpretation. Virtualization is really not, whereas interpretation is where I get to take one machine and have it behave like another. Virtualization is I get to pretend like I have many machines where in fact I only have one. Right? So it's a way of making a program believe it owns the machine when in fact there's another layer giving it its own simula of it. And then finally parallelism in many forms. And parallelism is going to be a lot of the talk that I'm going to give in terms of exploring and bringing this out, because it's in fact the area where I've spent most of my time and have sort of observations of what's been going on in that field. But let me, when I said that there's something going on here in technology and technology implementation, and this is Silicon Valley, okay? So, it was really about that, that growth of silicon. The special thing that happened in my mind was, just about 20 years ago, in the mid-'80s, we had, the classic technology of these so-called, microcircuits or discrete processors. So these are the way that Cray would go build supercomputers with ECL, or mainframe is built with a thermal conduction module. It's most of the big iron that you see in the displays here are basically things that have been on this curve. Okay, so they were discrete processor times. And if you went to 85, about the best one you would find was like a 250 megahertz system. And about the best microprocessor that you would find at that time was 33 megahertz. Is a little generous, but it's around in that area. So you can see the distance. The best performing systems were still the things that you would go craft with that very special, highly tuned technology. Now, what really happens here with this curve for people who know it, because as I said, I was out building systems on microprocessors back here in 1980 to run airplanes, right? And then before that, in sort of the mid-'70s, there were a lot of things happening. The 6502, that's the basis of the Apple, was what? It was a microcontroller. It was designed to run washing machines and microwave ovens if they had them at the time. Right? And in fact, as a computer architect, you go back and you look at this stuff back here, things like the 4004, 8008, 8086, hacked on a lot of that stuff. It was awful. It was really, really bad architecture. Right? And you look at it because there were a lot of concepts that had been developed in sort of taste in how you design instruction set architectures that really were not, for whatever reason, these people weren't doing. In fact, because they were going and building things that were trying to be controllers, that were trying to replace hardwired logic in systems and replace it with something that could be programmed, but not really thought that they would be general purpose computers. What happened here is you got close enough in 1985 and you could start adding the trappings and embellishment like, wow, what have we put in virtual memory or memory translation or caches? I mean, or how about some basic level of protection or abstraction? I mean, there are a whole lot of things that were awful, and missing that were coming in, but they were starting to get good enough. And then, you know, the physics of that miniaturization took off. And just by printing things on a chip, and this is where you go up, you know, this curve of 100,000, a million, 100 million. You know, it's more or less 20 times because it's probably about 400 million today. But if you follow this curve, well, we can talk about what's there. So what really has happened over this time is that there were a lot of these concepts in machine organization, things like pipelining and superscalar out-of-order execution, prefetching, speculation. And what we did is that we just sort of harvested those ideas and put them into the microprocessors. We taught the microprocessors these lessons that we had already learned and discovered. Some of it reinvented along the way. I'm sure there were many people who, you know, got a great deal of joy, and that's wonderful. It's part of the process of reinventing something that you then open up, you know, your textbook or go back to some papers of the time. Remember, the web was not alive and running, and most of that, and go find that Tomasulo had done that years and years ago. Okay. So, you know, one thing that I, as sort of an architect, sort of watching the pain of going through this process, of seeing us learn about this, I did, you know, come up with one principle of computer design out of that, which is don't let electrical engineers design processors. Right? So you get stuff that's like really handcrafted and bit packed and kind of cool and absolutely, you know, really difficult to program. And then if they're really good at it, if they're really creative, and it has very high throughput and all that, you saw that through the 80s. What you do is you'd call it a DSP, right? And I know what DSP stands for because at PictureTel I was designing these codecs, and we had to make them very programmable because we were, you know, trying to push the edges on these algorithms. DSP actually stands for destroys software productivity, right? And I want to show you. I have my own museum at home of artifacts, but this is the one of the processor boards from the original PictureTel codec in 1985. It's a bit-sliced array processor. We had 7 of them in the system. And so this was doing full duplex video and audio over 56 kilobit lines, right? And it took as much, we actually had to get more integer performance in this codec set than the Cray 1 was delivering at the time, right? And how could we do that for $100,000? Well, the miniaturization thing is that all 7 of these and all the software and algorithms that run on it kind of run in the corner of one of your, you know, your PC or Mac. Right now, so it's all software and it's all simple, and you know that's where those compounding factors of Moore's law make a lot of sense. So it's just a little opportunity to show and tell there. There's the other mistake you can make, and it's one that's been made many times. I told you with a lot of affection about programming the Burroughs 6700, which was at UCSD at the time. It was right at the time of Ken Bowles doing UCSD Pascal. It was a very exciting time because the first year I was there, I was doing Pascal on punched cards. The next year we had these LSI 11 systems and actually had the big 8-inch floppy disks that you put in. By the way, a little personal story for me is that when I went, I remember going to MIT and starting up in 1980 out there, and I was walking down the street, and I saw a 5 1/4-inch floppy disk sitting in the gutter. You know, it's like 1981, and I thought, you know, I was in heaven. I had arrived. What place? This is like streets paved with gold. You know, they're paved with bits. What place would have so much computing stuff that they could allow floppy disks to sit in the gutter? You know, and that was sort of the time for me of the rise of computing. And then just this last summer, I was out in New York City, and on the corner are people hawking compact flash cards and USB memory sticks. And now I know I've arrived. But if for people who've looked at things like the Burroughs 6700, it is a literal stack machine implementation, very elaborate, sort of looking at ALGOL as the language and how do we implement that that language. And it was probably the most pretty machine that should never have been built. You know, it was one of those things, and we get seduced by that. You know, there was a lot of things around like capability architectures and the like, and we went and built, remember the Intel 432, these very elaborate, they actually may have been way ahead of their time, by the way, since I think sort of trusted computing is going to become important. But there's a lot of sort of thinking at a very high level about computer architecture and languages, and then trying to get machines to do it. And sort of another conclusion I've learned through this is, don't let computer scientists design them either, right? So you get something really odd sort of coming out of it as well. And I think this is kind of part of this, the servoing technology. The electrical engineers have won because they've had kind of the technology at their back. And I think that, from my generation and the real value of what Hennessy and Patterson had done was really computer engineering. So how do you formalize the art of saying, I want to do this quantitatively and go figure out what trade-offs ought to be there. But in all of this, and I'll say this is sort of my major flameage that I deliver a lot at universities, is the big failing along the path is that we have different instruction set architectures now. I think it's a huge failure, right? Because the reason why it's a huge failure is that you get competition. For instance, you have these different instruction set architectures that are out there, from Intel-based architectures to Spark to Power to 390, and a lot of that has been culled down. Market forces has done that. But why it's a bug is because we write these applications in high-level languages, right? You can write in C or Java or Fortran or your favorite language. And in most cases, if you're saying you're writing a C program, in fact, what gets delivered is a binary, right? It's just like when you go buy software, you have to know whether you own a PC or a Mac. Why do you have to know that? Because they're different. And part of the problem of it being different is that, and the failure is, we write things in high-level languages, but we deliver and verify them as binaries. Right? And we have some real major abstraction failures going on now, where in order to verify something, you've got to verify all the bits down to the lowest level of even firmware in a system. If you want to run Oracle, and have it supported by Oracle, it's going to be on a particular tested vertical stack of implementation that violates every abstraction you can imagine, right, going down, because that's the only thing we know how to verify. And that's a failure. There shouldn't be multiple instruction set architectures around. We shouldn't care. It shouldn't matter. So I wanted to go back to this discussion that was a bit of flaming, but to talk about parallelism. And what is parallelism? It just says, look, that Moore's law and speeding stuff up and things getting faster, that piece of it. Moore really talked about the density, how many transistors you get on a chip, and what happens to that. Okay, chips get bigger, feature size gets smaller. It's about every 18 months. Didn't say things getting faster. What you do get to wonder is, at some point, when do I stop sort of this, I'm going to try to execute a set of instructions as fast as I can, and when do you sort of back off and say, I really want to try to do multiple things in parallel and not worry about making each one as fast? And I should say, just in my career, we went from when it was a real raging debate about whether you should think about parallelism in the large, whether multiprocessors were really the thing that you ought to go build. If you went back into mid-'80s, there was a very big debate, and a lot of people were looking for things like, what's the next superconducting squid thing to go make really fast computers? And you had people like, you have one of them down in the exhibit here of dipping boards in liquid nitrogen and the like. So this concept of parallelism has been one that has been is begrudging, and I would also say parallelism is also a bug, right? That if we had our druthers, we'd rather build really, really, really fast single processors because they would be a lot easier to deal with. All right, so we kind of deal with parallelism out of necessity, not out of that it's something really desirable. And if you look at it, it has this space that kind of divides into things that are so-called instruction level parallelism, where you look within an instruction stream as if it was a single processor running, but you look for opportunities to do things in parallel. That's like pipeline execution and multi-issue and speculation. But as we're growing now, we're saying we can't do that anymore. There's just not enough parallelism there to kind of feed the appetite of these systems. And so it's really at the thread level, meaning we want to take multiple programs that are running and be able to harvest that parallelism, not really multiple programs, but at least work within a very large program. And one thing that I studied under Professor Arvind at MIT, who's one of the big data flow pioneers, and Arvind always said that if the program is big enough and runs long enough, it has plenty of parallelism. And I believe that. But there was also a lot of debate, and a lot of the debate why around parallelism. Could you discover it? Could you see that it was there? Well, we've ended up in this era now with so-called embarrassing parallelism. I mean, one of the things that's happened and reshaped the whole architectural view is what the web has done. Because now we just have sort of infinite supply of work to get done. All you have to do is go over to eBay and sort of stare into the fiber optic pipe that's coming into the side of their data center and look at millions of requests that are coming per second at you. And a lot of those requests can be handled separately, right? They're painting each person's independent web page. Although curiously, you do get to a point where you have to join them, right? If two people are bidding on a blue Beanie Baby, then in fact you only better give one blue Beanie Baby out, right? So at some point you have to resolve that, and things like caching and coherence become very important. And I should add to this, is just from my own view, Burton Smith, who's actually don't know if he's CTO or president of Cray. I don't really know what his title is at Cray right now, but he has been the person I have looked towards as sort of really is the best sort of overall view about parallelism and how you use it. His view is you invest parallelism in essentially to hide latency in systems and to hide delay. And Burton's, this is actually a picture of the HEP2, but this was back in the 70s, but a multi-threaded multiprocessor, right? A real pioneering piece of work, something that has been very influential on me in that thinking. And then we get to parallelism, massive parallelism. This was really fun stuff. This is kind of the sort of mid to late 80s, where you had the CM2 in the upper corner, which is 64,000 processors, 65,000 processors, and very simple processors, a lot of them to a chip. And which you think about that, wow, in kind of the mid-'80s, somebody was designing a machine that had 64,000 processors in it. And then it's sort of evolved to a bigger cousin, which actually, for a very interesting way, is how I got to Sun, is the CM5 down there, which could go up to 16,000 processors. I don't think one was made that big, but that was actually using microprocessors, Spark microprocessors in this case. And as you see that really nice lightning bolt design, if it looks at all, evokes anything within you, the industrial designer on that was Maya Lin, who did the Vietnam War Memorial in Washington, D.C., and so you get that sort of look about it. The other thing that's homage in there is you see these the red LEDs on there. There was an LED hooked up to each processor kind of activity bit. So when the machine is running, you see all the lights, like very, very nice kind of sci-fi movie thing. I'll tell you a little story about the CM5 there. Those lights are also connected to activity bits on each processor, but indirectly. There's a microprocessor that runs each of those panels. It samples those activity bits and then relays them to that display. And so when a program's running, you actually get a lot of information off the lights, which is something that I know a lot of people get nostalgic about. But in fact, what was happening is that sometimes the machines would go idle, and people have paid many millions of dollars for these machines. So they sit in your data center behind a glass house, and the person who wrote these big checks have no idea what this is for, walks by for a tour, and they see the machine, and the lights are off, right? Or they're just like a stripe on or something like that. So we end up writing a program for this thing, which was would run the lights when the machine was idle. It was called the randomly pleasing pattern. You know, in 1994, which I think is kind of like the, if you're a computer architect, this was the burst of the dot-com bubble equivalent. Right? There was a huge amount of diversity in this case. You had people arguing, you know, should you, in the case of that, the 64,000 processor machine, you'd issue one command to all 64,000 processors, they would all do the same thing. That's a single instruction, multiple data. They would just do it on their own sets of data. It's very interesting architecture. There was the CM5 was a different organization. Every of those, you know, up to 16,000 processors ran their own program, but they would synchronize, and there was a lot of dedication put into the design of those networks to get synchronization. There were people who were arguing they should be shared memory machines rather than these. So you had things like Kendall Square Research and the folks out in Sweden at the Royal Institute working on you know, vast cache architectures with thousands of processors. Certainly the Yale work on VLIW and you know, transactional memory, Maurice Hurley and you know, still continue on to this day. Where I was, as Gordon Bell accused me when he was reviewing my project at MIT, in the backwaters of computing and on doing data flow machines, but I believe that will come back. And well, there. This collective communications, basically thinking about the problem of, you know, how do you do things like all-to-all exchanges, right? There's, in fact, Steve Heller, who runs our Burlington, Massachusetts, directs those labs reports to Glenn, is one of the masters of understanding the dynamics of, you know, what are the interference patterns when, you know, these 16,000 processors want to talk to these 16,000 processors in an interesting way. All right? And actually, all of this informed by a linguistic exploration, meaning there were languages around. There were things like data parallel Fortran, C star, star Lisp, the work that Guy Steele was doing in these areas. There's a lot of diversity and experimentation about what this ought to look like. This is also from 1994. It is from February of that year. It was a petaflops workshop at JPL that was prompted by the NSA that was beginning to worry that, you know, we weren't building machines fast enough, so they want to do petaflops, right, which is 1,000 times more than a teraflops machine. And I had really, it was delightful for me. You see, I told you 94, 10 years ago, my hair did start turning gray when I came to Sun. I'm there on the right. That's, you know, Seymour Cray in the middle. And then Burton Smith, as you see in the far right back. In my estimation, is the greatest living architect in computing now. And there are a bunch of other people there, like you know, Peter Kogi in there around you know, pipelining, et cetera, et cetera. I will share a story. We were the architecture working group, and Burton and Seymour and myself were split off into doing sort of the language mapping into the architecture, which was really fun because we didn't do any of the things we were supposed to do. And we just sat down and talked for a few days. Had a great time doing it, and then figured out, you know, that we ought to write a report or something. I don't know if I should be telling anybody who worked at DARPA at that time, but so I was very interested in, you know, trying to climb inside, you know, Seymour the best you could, because he would not do these kind of events. You just would not see him out at conferences or things very often. And I said, so what are you working on? And I'm waiting for the next great architectural innovation to come from him. And he says, you know, I've been really getting interested in cell biology. I'm like, oh, really? Tell me about it. He goes, you know, we've got little computers inside our cells, and they're digital. And every time this, you know, ATP, you know, kind of clicks along the track, consuming one quantum of energy, it kind of moves along in this way. And he's, you know, really into, he says, I want to, you know, I just really want to go do that. And it was really put together for me just right after that and talking to Tom Knight at MIT, who really has followed that path. Seymour, sadly, was killed a couple of years after this. But it was, you know, Tom Knight wants to teach bacteria to count. Right? How do you do that? How do you think about, you know, sort of going back to the TTL data book of that era? So, you know, trying to reduce down, you know, these architectural axioms that I've learned from this stuff, at least for that time, is you know, Cray, if you really tried to dig inside what he did, which was just some beautifully simple stuff, I mean, don't think that RISC machines were invented in the microprocessor era. They were not. They went really earlier than that. In fact, I mentioned Maurice Wilkes. Actually, Bob Iannucci and Maurice Wilkes held a seminar at MIT in about 1983 that was looking at what was happening with RISC. And we had people like Forrest Basket come in and talk about what he's doing with Titan. But if you went back, you would see those design patterns in the CDC 6600 and a lot of machines necessarily before. Glenn Culler, who is another, I think, unsung hero here, who really developed and pioneered a lot of array processing and sort of brought bandwidth in the equation. But Burton, is, hey, it's all about latency. He's been saying it for 30 years, and darn it, he's right. It's exactly what it's about. Latency is the delay. How long does it take you to go to memory and get something back? And the problem is that as things get faster and faster, if I can compute faster and faster locally, you look farther and farther away from me. Because relative to the amount of communication I can do, I can do a lot more computation than I can actually communicate. And it's basically speed of light. And I have to add one here, because I guess I am giving the talk. My sort of axiom is, tolerating latency is no excuse for introducing it. Right? And constant factors matter. I think you're seeing this played out today, and I'll say a little bit more about this. If you look at Opteron and why I think they did such a bang-up job with that design point, is the integration of the memory controller on the chip, and basically cut out about half of the memory delay that you see in a similar organization. And that's what it's all about today. So my kind of reflection is, and now I can start getting optimistic for you, right? Is that what happened from an architect's point of view? We've been more or less persona non grata, in a way, in that there was a lot of things around vector processing and then massively parallel processing. You see all of this sort of innovation and things that go along with it, and then this commodity hardware and operating systems happen. All right, that it's the things that like workstations and PCs and servers that you can gang together on networks. And I woke up to this in '94 when I was at Thinking Machines, and we were the biggest competitor we had at the time. I thought it was going to be something like Cray or SGI, some of the real powerhouses in design. At the time, building big scalable machines. We were starting to get our customers talk about these Spark 8 processor and 20 processor SMPs. They can only go up to 8 or 20 processors. We can go up to 4,000. It's like, well, that's fine, but it's maybe all I need right now. Okay? And look how cost effective it is. And so what actually happened is that this sort of good enough stuff, which is a story of reinvention in the business a lot in any case, started to happen. The other thing that happened is that it became really difficult to go build computer architectures from kind of, with a reasonably small team. If you were kind of back in these areas doing the real high-tech stuff to take big teams, but you could go to TTL. You could go buy these, discrete circuits and put them on printed wire boards or wire wrap, right? It was very accessible technology. When you saw why this was a peak here, it was really the ASIC revolution coming online. It was people like LSI Logic enabling a tremendous amount of productivity from people who were doing, sitting with the workstation and doing design. And by the way, another little flamage for people, and I know I'm at Sun, kind of like one of the workstation pioneers, but my point of view as a machine designer, workstations, bitmap graphics, I think, sent us behind by 10 years. Right? And the reason that happened is I'm very linguistic focused. I like languages. I like compiling things from languages. I think that's the way you ought to design hardware. This is the way we design hardware now. We were just getting at that point in the early 80s, right, where we were starting to use hardware description languages and doing compilation. Then come in these Apollo workstations and then the Sun workstations with the bitmap graphics on it. I practically died, right? Because what happened is that it let you draw the schematics again. And so they were electronic schematics, and it took us 10 years to figure out we shouldn't have done that. Right? But we did, and you know, sort of end up in this area. But now, here, it's really hard. I mean, if you want to go build a computer at the processor design level, you need a big team, because you're really designing a custom chip, and it's hundreds of people to go do that now. I almost feel like how it must have happened in aeronautic engineering departments in universities, you know, when you had your wind tunnels and you'd go build aircraft and all kinds of things all the time, and then you just couldn't afford to do it anymore. You just kind of do experimental stuff, and you know, sort of the Boeing and Airbuses of the world go do it. However, what is becoming accessible is being able to hook them together on networks, right? And that's becoming much easier for people to do, and that's why you see a lot of that energy in here. But from my perspective, what's happened is that sort of from an expressive point of view, from how do you program and approach the machines, in fact, it's stone knives and bearskin. We've kind of gone into this era of, you know, very explicitly trying to coordinate this work of hundreds or thousands of systems, and it's tedious. And it's like you're doing assembly language programming at the level. But do I believe that, you know, which way is this going to go now? I'm actually really optimistic. And I will give you some of that optimism. But this was my big lesson from the MPP era. It was these you know, multi-processor systems coming from underneath, like the Sun systems. You know, you can scale up, but if you can't scale down, it doesn't matter. Right? You have to be able to drive down to where the individual elements are themselves efficient and desirable. You can't sort of make it up in volume, right? And that's for me, has been one of the most important enduring lessons about looking at, you know, what will be useful architecture and what won't. Okay, so now back to this observation and what's happening now. And I think there's a big story unfolding in the business, and we haven't seen it yet. We're right on the cusp of it. It's scary and exciting at the same time, but it looks to me exactly like we're back in '85. And if you were back in '85 and having the risk discussions, what you were saying was that, you know, about 100,000 transistors on the chip, those transistors were precious. Okay? And in fact, you were doing things like putting floating point units and memory management units and caches off chip, but you know, the risk was, how do I use these precious transistors to go, you know, get a reasonable computer implemented? And once I got it implemented, I enjoyed the physics of those wires and I wrote it up. And again, we're harvesting all of those ideas that were back here that were done 20 years ago over this 20 years, right? I think you see where this is going. So we have these microprocessors in discrete systems, but now we're at the point of actually being able to print an entire server on a chip, entire computer on a chip. And for people, like, okay, maybe I'm weird, but I really like walking down in Fry's to see the motherboards and watch them kind of evolve over time. And one of the things that's kind of cool, if you're particularly the Palo Alto stores, you're getting close to the end, you know, that they get to the mini ATX form factors, the small ones, and now the micro ATX, which is just a little PC on a stick like this that VIA does. And one thing you notice when they get small is there are no sockets for the processors anymore. In fact, VIA has a 2-chipset implementation of a PC. And it's probably going to go down to 1. Right? And so we know you can start to see that. In fact, systems on a chip is an old idea. Right? It's one that goes back 10 years to things like, how do you think your mobile phone is actually made? It's a whole lot of integration on a chip. And that was done for a lot of cost reasons. It's exactly what happened over here in the microprocessor and in the embedded world. Right? And in fact, one of my side points to John and looking at the Computer History Museum is there has to be a lot more attention to, you know, embedded applications of technology, because in fact they drove a lot of, you know, sort of this resonance between the large-scale computer architecture and the embedded thinking is what actually has propelled this field forward, in my opinion. And that's really, I've slaved a lot of hours over Intel Blue Boxes for people who've done that. Writing code for 8086s. So we have this line up here. So at this point, you can actually build a very credible, complete server on a chip. Right? And it's only a matter of time now. See, if you went back to around 1990, this craft of building these discrete processors stopped. People just stopped doing it because it was more compelling to be on that curve. I think exactly is going to happen about 2010. Those motherboards are going to disappear. They aren't going to be there anymore, right? Because the craft of putting together discrete systems isn't going to be the craft anymore, right? The systems will be monolithic, and in fact, then it's about these discrete networks and how to really get a focus on networking. And you know what? I think it's the same thing. And this is kind of the optimism. We have learned a lot of computer architecture in the last 20 years. Now, a lot of these concepts are ones that people, again, thought about 40 years ago around cache coherency and symmetric multiprocessing and VLIW and multi-threading, but I think there have been real legitimate progress that's been made in that in the last 20 years. And in fact, we really will be harvesting these ideas as we move forward over the next 20. And I think it's going to be a very interesting time. And I have a little bit of a few sun slides on that. And of course, I wouldn't be excited about it. And we placed a really big bet on this in the company a few years ago and have completely redone our roadmap. This is the diagram of, in fact, a single chip server that we have that's called codenamed Niagara. And it has 8 Spark cores on it, and each of those cores is 4-way threaded. And there's, they have their own caches. There's a switch and caching control on there. And then you see also directly memory control and memory coming directly onto this chip of several tens of gigabytes per second of memory bandwidth. Right? And that's the system. It's up and running Solaris very nicely right now, as of about 4 weeks ago. And so what we really found is that we've got this other knob of parallelism at last, that what we had been doing historically is just taking a chip, we'd move to the maximum chip, we'd max it out with the biggest, baddest microprocessor we could build on it, consume lots of power, all right? But you actually realize that was an inefficient thing to do. If we got the processors, if we said, well, rather than just running a single program really fast, what if we allowed you to run a couple of programs at once, and then when this one's waiting on memory, we can run the other one. And that's a multi-thread single core design, and so that actually can give you a lift. We can get about a factor of 2 or so at times out of a core doing that. But then what happens if we back off? What if we don't build the biggest, baddest processor? What if we throw away a lot of the things that we learned to do with out-of-order execution and simultaneous wide issue? What if we went back to really simple processor design? All right? Well, we could put more of them on a chip. Well, let's run that experiment. What happens? Lo and behold, the performance is not being limited by how fast I can run the instructions. The performance is being limited by how quickly I can interact with the network or with memory. So if you turn that knob, we can do things like go to much smaller cores, but put more of them down, and sort of you get these multiplier effects. And it's like a factor of 10. And that's stuff that will keep you employed as an architect if you can get a factor of 10 by just rearranging the transistors on a chip. And I do believe it's back to the future, because it's the whole RISC thing all over again, which is the whole 6600 thing all over again. But one of the things that makes this work is, in fact, throwing lots of bandwidth at it. And I'll only just get you a bit excited about that. These are curves of kind of our big box machines, our highest end systems, Sunfire 15K, big refrigerator size, 72 processors in it, big bad thing, 58 gigabytes per second of memory bandwidth. We started a single chip at, as I said, a few tens of gigabytes per second of memory bandwidth, and we know what this server on chip sort of line going at. And then we've got some great innovations that are taking place at Sun on just getting chips to talk to each other without even wires, and what is that going to do? I just have a few attributions of these influence points. And I did want to talk about one thing, which was my machine. OK? So you're going to listen to it for a minute. So this was an outgrowth of basically data flow work. Right? So I'll start with that. But where we ended up, and this is work I did with David Culler and Ken Traub at MIT, was a very, very simple multi-threaded processor. Right? So we said, how could we get the absolute most simple processor design you can think of, which was you know, there's an accumulator, an instruction pointer, and a frame pointer, and that's it. There are only 3 registers. In fact, Dave Culler told me this story that his dad Glenn, and Seymour had corresponding, that Seymour got so frustrated with optimizing compiler work, or the lack thereof, on the Cray, that he had a design that he was asking Glenn to look at that just went back to an accumulator architecture and basically tried to do just renaming on the fly as deep as he and fast as he could possibly do it. And, you know, to hell with the compiler folks. So what a bit inspired by a lot of that is if you have that small thing, then in fact you just wrap it up. This is only 128 bits to represent an entire thread state. And then the threads point to memory, and the memory's tagged, thing that you're going to see come back now for a lot of security reasons, I believe. But there were presence of empty full bits on there. So actually, each processor was 256,000 threads. This was design started, well, 15 years ago. It had 8 simultaneous threads going, and I said full and empty bits. I could fork a thread in 0 cycles and do a join with a 1 cycle penalty. So packet switch network, and we built a number of machines and sent them down to places like Los Alamos. This was a big DARPA funded project, by the way. It's so lightweight in making a thread that if you wanted to do a memory request, you just forked a thread to go off to memory. And then when it finally got the value, it would rejoin your stream by doing a join. So it was a lot of fun. But let me make a couple of final observations in here. When you look at this from another lens of sort of what are the big organizational concepts taking place, you end up with this kind of, about every 10 or 15 years or so, something is changing in terms of our view of what's important in machine organization. And it kind of resonates off of some of the technologies that are building into this over time. And I thought this was a great original observation, and then somebody told me that they heard Gordon Bell talk about this years ago. So I'm going to call it Bell's law, right? But in this sense, if you really look at the mainframe in the 60s was enabled by the transistor and core memory. And that actually had the effect of really stabilizing instruction set architectures and what is a computer. And then the mini computers emerged because we had the small scale integration. We had the chips that people could go build boards like this with, right? That they could go do this kind of design and actually go build a computer using those fabrication techniques. And so that enabled the whole departmental computing revolution. And then as integration continued, and we got to these microprocessors, and then large scale integration, essentially that enabled the whole PC and workstation to take place, right, in the desktop revolution. And then we got to servers with symmetric multiprocessors in the 90s by this VLSI and DRAM. And VLSI was so we could really get enough of essentially logic of solving problems like distributed cache coherence problems in these systems. The other thing you should see on here is really what's happening in scale, with some exceptions, 1, 2, 4 kind of processor systems. They were really sort of unit scale systems and in terms of their processors, not really relying that much on parallelism. But as you started to get up into the symmetric multiprocessor era, we got to things like 64, 128 way shared memory systems. And now it's really interesting, because we have a very interesting conjunction here that's playing out, which are microsystems. So now we're reducing what we used to call a computer down onto a chip, and your crafting is around using those transistors. And then the intersection of the networking revolution with fiber optics. Because if I had more time to give the longer talk, which would put you all to sleep, it really would be talking about all the learning that's going on about computer networks in here, right? And how that's intersection. And the intersection is happening now. And we don't have a name for that yet, right? But it is machines essentially that are built from networks. So networks are their backplanes. What do those look like? And just as a graphic of that, here's a server, and this is the old systems are components in the new ones. That's a data center. It looks like a circuit board, which I find charming. I like that, okay? And that's the computer on the right-hand side. That's the scale we need to think about, finally. And what are the principles there? One of the things that make this work, I said about interconnect, we're at a very interesting time. I was giving talks up till about 1995 and saying why we were building these very specialized MPP networks. Really, just a fantastic amount of engineering that went into making the networks in the middle of a machine like a CM5. Was really quite pretty. But this line was what was happening with things like wired Ethernet. Ethernet was not keeping up with sort of the bandwidth. If people remember that, you had sort of 3 megabit, then 10 megabit. It took a long time to get to 100 megabit. That just was not scaling. Right? And I was complaining about it and justifying my paycheck on the basis of this stuff and working. And then fiber optics just came in with a vengeance. And it makes Moore's law look like a piker, right? You see these kinds of accelerations of gigabit, 10 gigabit, OC192, dense wave division multiplexing, put lots of colors down a fiber. And in fact, I think we're at this watershed. I look at 10 gigabits per second going down a fiber or down a color of light, a wavelength on a fiber, as a very interesting point, because it's an interesting amount of bandwidth. Even if you look at things like I told you, like a 10 gigabyte or 20 gigabyte memory system, you don't need that many fibers to equal that. But the other thing that happens is sort of this latency thing. If you're going across some large distance, that the speed of light is going to, say, 30 meters. The speed of light is going to hit you with something like 150 nanoseconds. But so does the serialization delay of a 256 byte packet. I always think that bandwidth is just a component of latency. It's a very Burton Smith kind of view of the world. And so, you get this kind of doubling at very high rates, and overhead gets pounded down, and basically we're now going to create these new computers. There are some really great questions. There are things like, what's the operating system for this? It's not, sorry, it's not Windows. It's Solaris, obviously. No, it's not any of those things, because all those things are designed to abstract the pipeline of the processor. That's not what we're trying to abstract here. We're in some distributed milieu. Well, the problem is that we haven't really thought about, what are the linguistic expressions that are up here. We know about how we organize things at a high level. It's not these. It's not the people. Okay, we got to automate that. Is it curious to you that sort of IT is the last place to get automated, in the sense that we all know it's the shoemaker's children goes barefoot, right? It really is horrible. I mean, every data center you go into is different from any other one, and you got thousands of people that are custom designing these homebrewed systems. I mean, it's fun, I guess, to some extent, but there's no scale economy at all. And I think that's really all these signs of wanting to come in. And I'm going to just skip over these because it's been a long talk. I will say that at the end, these are the things that I worry about now as fundamental issues. They're the fundamental distributed aspects of systems, sort of energy. I think that is going to become the concern. I'm often asked, what is going to be computing in 50 years? You get these questions of, well, we're at the 50-year anniversary. What is 50 years from now? I know it's entirely going to be an environmental question, right? And even today, it's not very pretty. We consume a lot more power doing computing than we should responsibly do. I don't know why Greenpeace isn't like all over the industry. Maybe because it's just too hard to quantify. Well, you got too many joules per op there, and we're going to run our ship in the harbor. But it's uncertainty and trust. And again, just begging off of time, let me just go through this. Had some real sort of thinking about the future, but I can go back with questions and talk about the slides if we get dull. But energy, there's a set of potatoes with the galvanic kind of cell there going and powering a little chip. I think that's the sort of the way that you have to think about it. Computing must ultimately be environmentally sustainable, right? And we have to think about those terms. And it actually turns out, right? You can communicate and compute with asymptotically zero power. It doesn't require energy to do computation. It requires energy to create or destroy a bit. But if you're willing to wait long enough, it's okay. It doesn't require much. So and actually Feynman postulated that in a very famous lecture in Japan. And Fredkin followed a lot of that up. The other thing that's happening in uncertainty, and not to get people really too concerned about it, but we're way into the quantum stuff now. And it's not just quantum uncertainty of, we got just a few atoms on a chip. It's the cosmic stuff. It's all of the Big Bang garbage that's hitting us all the time with these cosmic rays are making things at this scale very uncertain. And why do you have parity at ECC on your memory? Is because those exploding supernova have been sending their bits your way and upsetting your memory. And you know what? We're at the scale now where it's upsetting everything in your processor. You just don't know it. Okay? And I'll end with this. If IP is the backplane, then the whole internet is the computer. And finally getting to this, I think we're going to go in a period of time now that is going to be extraordinarily exciting in terms of the scale of systems that we're going to comprehend. Right? And you have to look no further than up the road at Google and see them with 200,000 or 300,000 processors, crunching away on an interesting problem to all of us. Right? Those are the contributions to computer architecture I think the new generation will be making now. So thank you very much.
For those of you who ask questions, please state your name for the record. Hold the thing in the middle, not by the end, which is its antenna. And please hold it close to your mouth. Every inch matters.
Yes.
I'm Ivan Goddard from Out of the Box Computing. It's interesting you mentioned the Brosby 6500 or 6700.
Yes.
The first compiler I ever did was for the Brosby 6500.
Oh.
And there are some numbers that might be of interest to you in that effort and is relevant here.
Please.
We did the entire operating system, 5 major compilers, and all the ancillary software on a brand new instruction set architecture with 18 people in 2.5 years, counting the secretaries and management. Furthermore, when we first got the first prototype hardware turned over to software for actual trial, we had a compiler compiling the operating system under operating system control on the prototype 2 weeks to the day after we got the hardware.
Wow. Wow.
Now, you can't do that today.
No.
And why is that? We have a processor breakthrough that's a 10x monocore advantage over anything that's available now. And we're having a real hard time finding partners. Why? Because everybody has this enormous lump of legacy software that just sits there like a bunch of old oatmeal and plugs up advances in architecture. How are you going to get past the oatmeal?
Yeah, there you go. Good question. By the way, let me pay tribute to you because it really was, for me, I cut my teeth on that system and an operating point of view. For people who don't know the Burroughs, it was Xalgol was the system language, and MCP, the master control program, was the operating environment, which was a beautiful piece of code, right? Because it would. We would always talk about, I was an operator on an 1800 and did stints on the 6700 as well, that it was a dual processor system. One processor would fail, MCP would figure that out and would take over the work. We'd figured the program would keep running even if both processors had failed. I will tell you a little trick I learned because I was writing a lot of interactive code for it, which was hard in those days. It was a system that had segmentation but no paging. Okay? So it would have the Swiss cheese problem in memory that you would, if you needed a big segment, a big block of memory, it had to wait to move some other people out so it would get to big enough space for you. That would be bad for your response times. So I did something very evil, which is I took my program and I busted it up in a whole lot of very small little pieces and submitted it that way. And in fact, what happened is it just got sort of lodged in places where the operating system wouldn't worry about it, and I just occupied memory the whole time. And it was, anyway, but I'm sorry to digress on that. It was just what a great system that was. But as I said, this binary compatibility is this big bug. It is that big weight that holds a lot of it back. There are some interesting things that are happening. If you look at least now where people are writing software, if you're writing that in Java or in a Java stack, or you're writing it in .NET on a .NET stack, you're actually executing on a virtual machine. You're doing that on a Java virtual machine doing bytecodes, the same thing on a common language runtime on a Microsoft system. And we could trace back and see where that happened with P-code interpreters and a whole bunch of things in the past. So there's a lot of history to that. But I think we're going to get to the point where we're finally going to get free of instruction sets. And one of the interesting parts about it is that if you write a new web-based program, if you're authoring HTML or you're writing database, SQL or something, your distribution as a programmer doesn't have any binary in it at all. No processor binary. That's a good thing. I think what that will do is reopen innovation in processor architecture, because there's an abstraction layer that allows smart people to go off with small teams and do exactly that. Yes?
Yeah, I'm Strata Chalup. I'm one of those IT people. You knew we were in here somewhere, didn't you? Now, you've made some very good points about processors and about the evolution of various axes of performance with different definitions. However, a processor-oriented view is naturally atomic. Your critique of IT is, in some senses, saying that we make the best cinder blocks in the world, and we've got to get rid of all those annoying people who just scurry around making buildings out of them. Right. How do you intend to move forward past that?
Well, you're at exactly the issue, precisely the issue. Thank you, and it was a really good way to put it. We are, in some sense, missing the forest from the trees here. It's not about the processor architecture anymore. It's about the organization into these larger systems. And largely, we have not had any guidance at all from the computer architecture community on how you ought to construct these buildings. So it's kind of an exercise left to the user while we've been sitting there working on the components. And I think that the one reason why this sort of microsystems thing gets me excited is because it's going to destroy the ecology of the computing industry the way you know it. Become very transparent. There are only a few places that are going to design computers. Those are the people who sit there and paste transistors down on silicon. That's it. And so the rest of the industry better figure out what they're doing. And those are components that you use to build these bigger systems. And we have to get regularity around it. Okay? It's why the utility or service model is going to happen. Okay? The thing that really drove computing in the late 80s and 90s, and the great innovation of Microsoft, and I think the real genius there was shrink-wrap software. Right? I can for $1 or $100, I can buy a few $1 billion worth of R&D or a few $100 million worth of R&D. That's a great thing. When I go get a computing service, I ought to have the same thing. It should be that every dollar I invest in the service is buying me millions of dollars of R&D and not buying me just $1 worth of some professional service time.
Hi, this is Rama from Sun Microsystems. Hi.
Better be a friendly question.
Yeah, sort of.
Okay.
Two unrelated questions, but the first one is about your other interest in search for extraterrestrial life.
Yes.
Could you talk about that? And the second part, what are you working with Bill Gates on? Could you share?
What is it? Well, I better not answer the second one too much, but the first one I'm happy to say real quickly. I'm actually the chairman of the board of trustees of the SETI Institute in Mountain View. We're neighbors here, and it's just a wonderful institution that both is doing, some just great dedicated people doing the question you have to ask. If you don't ask, I don't know, what other question you would ask, but are we alone? And how do you just try to look for technology artifacts through radio signals? The other part of the institute is just looking at life in the universe, and what does it take to get life to happen somewhere, and how does that evolve? And it's just a really interesting, passionate thing, and I invite anybody to get involved with that. So, and Bill Gates is coming here on Friday, so somebody ask him that question.
Your name for the record? No, it's Brad Templeton. Actually, just to, now this is the SETI League, not the SETI Institute, but
yes.
There actually is an alien intelligence already here on the Earth. It's a computer intelligence, and it's masquerading as a program that searches for signs of intelligence.
Yeah.
And that was the only way it could get enough people to run it in order to have the power.
Yeah,
so that's my theory. I wanted to challenge your statement about architecture in terms of the oatmeal. Because in fact, if you want to move a program from one machine to another today, moving it from one architecture to another, that's irrelevant, that's nothing. That's no work at all. Right. It's the APIs of the operating system, and I won't name an operating system by name, but there are some operating systems that have basically extended the operating system into a collection of thousands of DLLs, not that I'm naming the operating system. So that the operating system has become much more than what we typically define as an OS, and that's one of the results that makes it that the APIs are really the challenge there, and it's nothing to do with architecture, so I guess, I don't know, you seem to agree with that, so then where do you take your conclusions from that?
Well, look, okay, first I want to have a little quip about this, intelligent life searching around for things here too. One of the big thresholds in computing, it was my aha in, when I saw my first Sun 1, right? It was at Honeywell at the time. It was in very, very early 80s. And I was sitting there, and we were using these time-shared multi-systems. And you would, every time, remember that? You'd use the systems, and then you'd log off, and it would tell you how many dollars you burned in your account. Right? And then you sit down at this workstation, you just use it. And when you were done and you logged off, there was no how many dollars you just, right? And it really occurred to me, it was, there was a huge watershed at the point when your perception that your time was more valuable than the computer's time, right? And I think that was really the definition of the, sort of the computing revolution in my mind. When did people think their time was more valuable than computing time? And now I might say as I look towards the future and you...
By the way, I spend a lot more time sysadmitting now that my time is...
Yeah, that's right. Yeah. Now, how have you been enslaved as a computer operator is another question, right? But, I actually think the interesting thing will be as we go in the future and we finally go crack AI, right? At some point that's going to happen, I guess. Right? I think the other interesting watershed is when the computer finally decides that its time is more valuable than yours. Right? But now I've really forgotten your other question. But look, here's one of the dirty secrets of the computing industry. I know there are people in the press here, so I'll probably get quoted in one way, unless I'm being very obscure about it. But we live on locking in customers. That's what it's about. Because what you do is you go create, essentially, a switching cost. As you said, you can port things around from architecture to architecture, but it's really the cost of verification or some other entanglement, like a state entanglement. I mean, if you tried to move your state, like upgrade a laptop, it's hard. Why is it hard? Because you're insinuated in this thing with all the state that's in there, and you've got to sort of, invert it and put it back out. And it's almost like this non-Markovian process that depended on the path you took, And so you're in this point where essentially what happens is that these locks create switching costs. And switching costs always create market friction, and market friction is a source of margin because it raises the activation energy for somebody to change from platform to platform. And a lot of this has to do, it's back to the IT question, is that as we get to designs that really are at network levels and we get to the next level of abstraction, as an industry, shame on us if we don't finally cure this problem of this abstraction layer, or at least make it a lot better, and reduce switching costs and get things to be much more commodified, which I think is a great thing, right? And it's just a matter of going through it systematically and making sure that we sort of adhere to these open interfaces. Yes?
Richard Probst, SAP.
You spoke about the descent into the dark ages of
Yes.
commodity hardware, and I wonder to what extent that was driven by government funding decisions, and in line with that, how you think industrial policy in computing and communications is going to drive the evolution you were talking about.
Yeah, there was clearly a case there where there was, it was a monopsony. You know, the monopsony, you have a, essentially one buyer, right? And so the government was that buyer. And there were many more companies that were started than that could have been sustained in terms of the consumption. And maybe not unlike the dot-com thing in that way. And so a lot of ideas, I know at Thinking Machines, we were running, kind of, $100 million kind of R&D rates. But that was the revenue rate of the company too. I mean, you just couldn't, you couldn't break out of that. So there was in some sense that it was overstimulated. I think that people learned some lessons from that. By the way, the Dark Ages, I'm totally for the commodity stuff. I think it's great what's happened from a technology advance in that point of view. Don't misinterpret me. But it has been the case that the architectural side of it has languished at the parallel level as a result of it. All right, what happens now in terms of policy? I think there's a very interesting balance now where things are trying to be stimulated from a national competitiveness point of view, but people all realize that you better have a bigger marketplace for your wares. Yep. Are we there?
I'll ask one.
Okay.
John Green here. If electrical engineers shouldn't do architecture and computer scientists shouldn't, how about model railroad clubs?
Model railroad clubs should do computer architecture. Thank you. Thank you.
Greg, thank you so much. That was terrific. You've come a long way since those monsoon days.
And Greg, we have a small token of appreciation for you on behalf of the Computer History Museum and Son.
Thank you very much.
And Glenn, thank you very much. Thank you, everyone. Hope you enjoyed yourself. Greg will probably be around for a few more minutes. Remember, our next series in the series will be October 20th. Thank you.